In this example, we're asked to find the orthogonal projection of t cubed onto the span of the polynomials p0, p1, and p2. Well, above here, you'll see that it says let p0, p1, and p2 be 3, 2, and t squared minus 2 respectively. And the thing is, when we're projecting onto the span of polynomials or vectors or what have you, and by the way, we can treat these as vectors, we need to know what the inner product is. If we're not told, we just assume it's the dot product, where you just multiply the components and add up. But here we're actually told the inner product is defined as p comma q, where we do p evaluated at -2 times q evaluated at -2 plus p evaluated at -1 times q evaluated at -1, etc. up until 2. And you could say this is the inner product with evaluation from -2 to 2 on integers. So first things first, we're finding the orthogonal projection of t cubed onto the span of p0, p1, p2. And one thing that's very crucial here that students often forget is that the formula I'm going to use here only works if these guys are orthogonal. Let me write down what that formula I would like to use is, and that's that the projection of, let's call it capital U, just some space, and then a vector y, is the first component of that space, inner product with y, over the inner product of the first component of that space, comma, first component of that space, times first component of that space, and then you do that for each component. The thing is, this only works if this set right here is an orthogonal basis. If it's not orthogonal, we have to do something else. So before I start, I want to verify that p0, p1, and p2 are all orthogonal to each other. And how do I do that? Well, two vectors, polynomials, what have you, in some space are orthogonal if the inner product is 0. So what I need to check is, first of all, does p null equal 0? Well, let's see. P null evaluated with itself. I'm sorry, not with itself. We want to check if each of these are orthogonal to each other. So I want to check if p null with p1 is orthogonal. So I'm doing the inner product, p null, p1. I find it easier to multiply these together first and then evaluate, as opposed to evaluating and then multiplying. And notice, if you remember how functions and polynomials work, that's totally legitimate. I'd plug in the value for each one of these and then multiply, or I'd multiply and plug in the value. I'll get the same result. So this is going to be 3t, 3 times t, evaluated from -2 to 2. And that's not standard notation. I'm just kind of noting how I'm thinking of this. So this is 3t times all of this. Well, this is 3 times -2 plus 3 times -1 plus 3 times 0 plus 3 times 1 plus 3 times 2. Now, I would encourage you with these problems, sure, you can just multiply these together, and then add everything up and see if you get 0. But I would encourage you, what if you have really, really messy numbers? That's a lot of room for error. Look for some obvious things that are the same. So for example, 3 times -2. That's the opposite thing in sign to 3 times 2. So those are going to be 0. Likewise, 3 times -1 and 3 times 1 are opposite. Those are going to be 0. And 3 times 0 is 0. So that comes out to 0. So now I know that p0 is orthogonal to p1. I would encourage you to do that as much as possible because it saves you a lot of time. All right, let's do p0 with p2. Again, I find it helpful to multiply them together first. So if I distribute the 3 in here, I'm going to have 3t squared minus 6. And again, I want to evaluate this from -2 to 2. So I have 3 times -2 squared minus 6 plus 3 times -1 squared minus 6 plus, let me save some time here, 3 times 0 is just 0, so that's gone. So plus -6 plus 3 times 1 squared minus 6 plus 3 times 2 squared minus 6. Now this one's a little trickier. Since I'm squaring all of these, I know that they're not just going to cross out. They're not opposites in sign. So in this case, I just do need to kind of combine everything together and see what I get. But I will still use some mathy tricks as much as I can. This is 3 times 4. This is also 3 times 4. So these guys together is 6 times 4. This is 3 times negative 1. This is 3 times 1. Well, in those cases, we just get 3. So that's 3 plus 3 is 6. And now look at how many negative 6s I have. Negative 6, negative 6, negative 6, negative 6, negative 6. I have 5 negative 6s. So this is negative 6 times 5. And again, yes, you could just punch this in the calculator or mentally like do out what these numbers are and see if it adds up to 0. These are just little tricks that speed it up. Ooh, 6 times 4 plus 6. Well, that's the same thing as 5 6s. So 6 times 5 minus 6 times 5. Hey, that's all 0. I never win above one-digit numbers. Haha. So P0 is orthogonal to both P1 and P2. Last part, I just need to check if P1 and P2 are orthogonal. P1, P2. Again, I find it handy to multiply them together first. So let me do that. This becomes t cubed minus 2t. We're going to evaluate from negative 2 to 2. Now, the trick I'll use here is that since this is the sum, it's a difference really, the difference of two terms, I can actually just evaluate everything on t cubed and then everything on the minus 2t, and then it'll speed me up a bit. So for t cubed, we've got negative 2 cubed plus negative 1 cubed plus 0 cubed plus 1 cubed plus 2 cubed. And then the minus 2t, we've got minus 2 by negative 2, minus 2 by negative 1, minus 2 by 0, minus 2 by 1, minus 2 by 2. And once again, negative 2 cubed and 2 cubed. When I cube these, I get opposite signs, so those cancel off. Negative 1 cubed and 1 cubed cancel off. 0 is just 0. Negative 2 by negative 2, negative 2 by 2. Same thing, opposite signs. They cancel off. Negative 2, negative 1, negative 2 and 1. Same thing, opposite signs. And negative 2 and 0 is 0. So this is just 0. So I've established that P0 is orthogonal to P1, and they're both orthogonal to P2. Okay, so now that I've verified that, and as long as that seemed, remember again, I'm explaining this, so it's going to feel longer. When you actually learn it and are comfortable with it, it goes much quicker. But it's very important that you have to check this. In this case, this worked out, so I'm going to be able to use this formula. But if this was not the case, that these guys were orthogonal, you would actually have to create an orthogonal basis and use that instead in order for this formula to work. So I just want to make that very clear. All right, give me one moment to erase all of this, and we'll be right back. Okay, now that that's erased, let's go ahead and compute the orthogonal projection of t cubed onto the span of these three polynomials. So I'm going to be doing the inner product of t cubed with the first polynomial, t cubed with the first being the polynomial with the subscript 0. So t cubed with the 0 polynomial, t cubed with the 1 polynomial, and t cubed with the 2 polynomial. Now, since in this formula I'm going to have these things right here, it would probably be a lot more convenient for me to just compute each of these individually on the side. So I'll do that. So first things first, let me do t cubed. Yeah, so let's do p null, which is 3. So p null with t cubed. Let's see what that is. So I've got 3 times t cubed. And we're evaluating that from negative 2 to 2. And this is a cubic function. So as you saw before, when I plug all these in, I'm just going to have 3 times t cubed, and I'm going to have negative 2 cubed plus negative 1 cubed, etc. And you can already see this is going to come out to be 3 times 0, which is 0. That's cool because that means that the numerator here is 0. So I'm not going to bother computing p null inner product with p null because that's what would go down here. Because I know it's 0 over whatever, so this is just, I don't even care. Don't need it. That's going to be 0. Let's go ahead and compute p1 with t cubed. Well, p1 is t, so t with t cubed is t to the 4th. Evaluating that from negative 2 to 2. So I have negative 2 to the 4th plus negative 1 to the 4th plus 0 to the 4th. And now, if I put plus 1 to the 4th, negative 1 to the 4th and 1 to the 4th are going to be the same thing. So what I can actually do is just multiply this right here by 2. Likewise, when I put plus 2 to the 4th, it's going to be the same as negative 2 to the 4th, so I can just put 2 times this. So negative 2 to the 4th is positive 16. And then 16 times 2 is 32. Plus 2 times negative 1 to the fourth is just 2. So that comes out to be 34. And now, in the denominator, I'm going to need P1, P1. So let's do that. P1 is t, so tt is t squared. Again, from negative 2 to 2. So I'm going to have negative 2 squared plus negative 1 squared plus 0 squared. And then the exact same argument up here. It's an even power. So 1 squared is the same thing as negative 1 squared, and 2 squared is the same thing as negative 2 squared. So when I do this, 2 by 4 is 8, 2 by 1 is 2, 8 plus 2 is 10. So I've got the projection of y onto u, one of the first terms, or the projection of t cubed onto this span anyway. The first term is going to be 34 over 10 times, what was I projecting t cubed onto? P1, so that's times t. So that's my first term, and I'll simplify that in a bit. Let's go ahead and get the next one, finally t cubed onto P2. So P2 with t cubed. Distribute the t cubed in, so I get t to the fifth minus 2t cubed. Notice both of these are odd powers. So what's going to happen is I'm going to have negative 2 to the fifth minus 2 by negative 2 cubed. And then negative 1, so plus negative 1 to the fifth, minus 2 by negative 1 cubed, plus 0. And when I get over here, I'm going to have plus positive 1 to the fifth, minus 2 positive 1 cubed. So these are going to be opposites, so this crosses out. And then I'm going to have positive 2 over here, negative 2 to the fifth and positive 2 to the fifth cross out, negative 2 to the cube and positive 2 to the cube, multiplied by whatever, cross out. So this whole thing comes out to be 0, which means I don't care what the P2 value is because I know the numerator is 0. So actually, there you go. If I just reduce this, this becomes 17 over 5 times t. And so that is the projection of t cubed onto the span of these three polynomials. So what does it mean? Well, if this is my orthogonal basis that I'm using, then the closest thing in this basis to t cubed is 17/5 t, which is kind of interesting. Before I end this, let me just kind of show why that makes some sort of sense. Remember that a linear equation looks like this. A square equation looks like this, assuming the coefficients are positive. A square equation looks like this. And a cubic equation looks like this. So even though it may feel kind of strange that the best approximation to a cubed function is just a line, we'll compare that with the parabola. Actually, the line, if I choose it right, has, again, if you stand very far back, has more of the general shape of the cubic function than the parabola does. The parabola matches a lot better on one side, but is totally off on the other side. Whereas the line actually is, kind of centered on the cubic function a bit more. So I just mentioned that because that tends to throw students off of like, wait, we're projecting t cubed and we get just t? Assuming that they're thinking this much about it, which you should. But there we go. The projection of t cubed onto this space is 17/5 t. There's kind of an intuition for why. Do not forget to check that you actually do have an orthogonal basis, because if you don't, there's even more work involved. But it's better to do more work and get the right answer than less work and get the wrong answer. So there you go.